complete proof system for one-free regular expressions, modulo bisimilarity. I'm Clemens Grabmayer from the Gran Sasso Science Institute in L'Aquila, Italy. Welcome to my talk about joint work with Van Fokkink from the Free University Amsterdam, the Netherlands. So there are basically three elements in the title: a complete proof system, one-free regular expressions, and bisimilarity, which hints at process theory. I will start with explaining these terms to you, starting with one-free regular expressions. Then I will explain to you Milner's process interpretation, and in particular his axiomatization question from 1984 for a particular proof system. Rather than solving the completeness problem for this proof system, we only obtain a partial solution, but one for its adaptation for one-free regular expressions. And that is a system that has been studied before us by Bergstra, Bethke and Ponce, three colleagues from Amsterdam, and the system we call BPP. I will explain to you why a classical proof approach to completeness fails and which approach we choose instead. The approach we choose is one that uses a graph property that we call layered loop existence and elimination property, LLEE. And then I want to explain to you the main lemmas of our completeness proof, where the most important one is the one that states the preservation of the property LLEE under bisimulation collapse. With these lemmas, I then want to explain to you, show to you a dynamical version of our completeness proof. And finally, I want to explain to you the intuition behind our proof of this main lemma concerning the preservation of LLEE under bisimulation collapse. Regular expressions, as defined by Kleene in 1951, in a modern formulation can be viewed as follows. We have a constant 0, a constant 1, we have letters over a given alphabet, we have the possibility to form sums, products, and binary Kleene star interpretation. So note, Kleene himself used a binary star operation. Only later in 1958, Copy, Elgot and Wright used unary Kleene star operations to simplify this grammar, and that then made it possible to drop the 1, which then namely is definable as 0 star. However, with binary Kleene star, 1 is not definable in its absence. And that makes it possible to also view the non-trivial subclass of one-free regular expressions that are formed according to Kleene's grammar, but dropping the 1. We will also speak about regular expressions as star expressions, and in doing so we follow Milner, who used that for regular expressions under his process semantics. He interpreted 0 as the deadlock process, 1 as the empty process that can immediately terminate, letters as atomic processes, atomic action processes that terminate afterwards. He interpreted plus as alternative composition between processes. He interpreted product as sequential composition, so first the one process, then the other. And he interpreted unary Kleene star as unbounded iteration of the underlying process with the option to terminate before and after each iteration. So then Bergstra, Bethke and Ponce interpreted binary Kleene star as unbounded iteration of the left part with the option to continue before and after each iteration with the interpretation of the right part of the Kleene star expression. Let's look at an example. Here you see at the bottom a one-free star expression and its process interpretation. That consists of an outermost binary iteration of which the exit is cut off by deadlock, so that leaves no trace in the process graph. but it starts with an A and then continues with an inner binary iteration which starts with an A and then can continue with a B back to where it started, or with a B and an A stop also back where it started, and then always the option to take a C exit. This is we call a chart interpretation, and in doing so we also follow Milner's terminology, who used it for process graphs. Here you see a somewhat more complicated 1-3 star expression and its chart interpretation, which consists of the interpretation of an innermost binary iteration here in red, a binary iteration in the middle in blue with an B exit, and an outermost iteration whose interpretation here I drew in brown. And on top there is an A step from the start vertex that is labeled with a brown arrow on top. These two charts are bisimilar, meaning there is a bisimulation between them in the sense of process theory, a binary relation that relates the start vertices and that makes it possible to simulate steps in one chart by an appropriate step in the other, such that the targets are again related. In the sense of bisimulation, these two charts show or realize the same process behavior, and that we can now pull back to star expressions and then say two star expressions are bisimilar under the process interpretation. And for that we use the sign which you see here at the bottom. The process interpretation has different properties from the standard language interpretation. And the most striking phenomenon is that there are finite process graphs that are not expressible modulo bisimilarity. And you see here two examples of such process graph. On the left hand side, one with an A-B loop and a sync termination vertex drawn in brown at the bottom, and on the right you see a chart with 3 vertices that are linked by transitions where all of the labels of the transitions are different. We will come back to both of them in a second. Fewer identities hold for bisimilarity under the process interpretation than for language equivalence, which can be seen very well if we look at Salomaa's complete axiomatization of language equivalence and then highlight those identities that do not hold under the process interpretation. And one example here is famously A5, left distributivity, which does not hold under bisimilarity famously, and also A8 does not hold. That is the axiom which would say that a process that is continued by deadlock would always be bisimilar to deadlock. Well, that's not the case, and Milner noticed that and dropped these two axioms, but he took up the converse, which is sound, and he came up with this system. And of this system he asked, is it complete with respect to bisimilarity of the process interpretation? We are not solving that problem, but instead we are adapting the system by highlighting occurrences of 1 and then either dropping occurrences of axioms that include 1 or changing them by stepping over from unary to binary Kleene star axioms. Also, the fixed point rule at the bottom loses its side condition. This then is the system of Bergstra, Bethke and Ponce, and of this we show that it is complete for bisimilarity on 1-3 star expressions. Now, let's come back to the non-expressible chart. Every chart can be seen as having an equational specification that it induces. And in doing so, we take variables for each of the vertices and let every vertex, according to its outgoing transitions, define an equation. You see the corresponding equational specification here on the right. Then Milner already showed that this equational specification is not solvable in his system or in BBP, which means the following. It means that there is no star expressions, no vector of star expressions that can be substituted for the vector of variables, such that the equations that you would get are valid equations in BBP or Milner system, are provable equations in the system. This fact is necessary for understanding the next slide, on which I want to explain to you why Salomaa's proof approach does not work in our case. Here you see examples of two star expressions and their associated process graphs, which are bisimilar. It's quite easy to see. Now, the classical proof approach would form the product charts of these two charts, which you see here on top. And now notice that this product chart on top has the outer form of the non-expressible chart that we have already seen. Note that here the transitions are different from the not expressible chart, but still it holds that if it would be possible to extract a solution via an elimination procedure from the specification of this product chart, then it would also be possible to extract a solution for the non-expressible chart. This is not possible. A solution cannot be extracted here directly. So we have to choose another way. And an alternative would be to go downwards instead of upwards, go downwards to the bisimulation collapse. In this case, we get a quite easy chart where that is quite obviously solvable. A solution can be extracted directly here. That is quite easy. However, the question is, can one always extract a solution directly from the bisimulation collapse? We will show that this is the case by using a property that we call LEE, which will guarantee solvability of charts. And we will also show that the chart interpretation, all chart interpretation have this property, and it stays preserved when going over to the bisimulation collapse. In order to explain this property to you, I first have to explain to you what a loop chart is. A loop chart is a chart with three properties. First, there is an infinite path from the start vertex. Second, every infinite path from the start vertex returns to it. And third, termination is not possible. If one looks at this example, then this is not a loop chart. Why not? There is an infinite start, so L1 is true, that is true. However, there is an infinite path marked in red, which gets lost inside and which does not return to the start vertex. Here marked in red. So L2 is violated, and therefore this is not a loop chart. The first non-expressible chart that we have seen is also not a loop chart, although there are infinite paths in it, and every infinite path would return to the start vertex. However, there is termination in its mid, so L3 is violated. This is not a loop chart. If we look at the first chart and change the start vertex to the bottom vertex, then this is a loop chart, because now all infinite paths, of which there are infinite paths, return to the start vertex V2, and there is nowhere termination. So this is a loop chart. Also, if we change the start vertex to V1, then this is also a loop chart, because all infinite paths return to V1. There are infinite paths, and there is no termination possible in this loop chart. Then there is also the notion of a loop subchart. A loop subchart may be created by picking a vertex and picking a number of entry transitions and then going further until the newly picked start vertex is reached again. So this is a loop subchart. And now I can explain to you the loop existence and elimination procedure. Look at this chart. In boldface, I have highlighted a loop entry transition, so an entry transition of a loop subchart, which can be eliminated by dropping it and performing garbage collection. Here I have immediately marked again a new loop entry transition. It can be removed again. And then we arrive at this chart, which can't have any loop subchart anymore because it does not have an infinite path at all. We could have removed loop subcharts differently, for instance, in this way as drawn here below. One step, a second, a third, and then reaching again a chart without an infinite behavior. Now I can explain to you the property LIE, loop existence and elimination. A chart has this property if repeated elimination of loop subcharts leads to a normal form that does not permit an infinite path. So the two non-expressible charts do not satisfy this property because they do not have loop subcharts at all, but they still have infinite paths. However, in the example that we have just seen, we have seen two successful runs of the loop elimination procedure which lead to charts that do not have infinite paths. So this chart has the property LIE. And if we now mark on this chart loop entry transitions in the order that we have eliminated them by additional labels, then we get this enriched chart, and here we get this enriched chart. Such enriched charts we call LIE witnesses. Witnesses of the fact that the loop elimination procedure has been successful and witnesses the property LIE. We give a formal definition of such LIE witnesses, and those are the basic ingredients of our completeness proof. Charts that have LIE witnesses we call LLEE-charts. The second L here stands for layered, so this is a subclass of witnesses that satisfy LIE, which is sufficient for our proof. And on the basis of this notion, I now can explain the completeness proof to you. For this, we use 6 lemmas. The first and most crucial lemma is that the bisimulation collapse of a LLEE-chart is again a LLEE-chart. The second and the third is that the chart interpretation of a one-free star expression, E, is a LLEE-chart that has a provable solution with start value E. A provable solution, recall, is a vector, and by the start value we mean the value of this solution vector that corresponds to the start vertex of the chart. And then there are two crucial other lemmas, E and SE, where E says from every LLEE-chart it is possible to extract a provable solution, and SE, all provable solutions of LLEE-charts are provably equal. There is one more lemma, but I will explain that to you on the next slide. Now, the completeness theorem says that the system of Bergstra, Bethke, and Ponce is sound and complete with respect to the process interpretation of one-free star expressions, meaning that E1 is provably equal in BBP to E2 if and only E1 and E2 have bisimilar process interpretations. Now let's prove that on the basis of the lemmas that I've shown to you. Let's assume that E1 and E2 are one-free star expressions with bisimilar chart interpretations. Then they have the same bisimulation collapse. This also means that there are functional bisimulations from C of E1 to C0, the bisimulation collapse, and a functional bisimulation from C of E2 to C of E0. A functional bisimulation is a bisimulation which is the graph of a function. Now we can use the fact that chart interpretation of regular expressions are LLEE-chart, so C of E1 is a LLEE-chart and C of E2 is a LLEE-chart. Then we use that E1 is the start value of a solution of C of E1, and E2 is the start value of the solution of C of E2. I've abbreviated that in the picture. Now, importantly, we use that the bisimulation collapse of a Lie chart is again a Lie chart. So C0, the bisimulation collapse, is a Lie chart. And now we use the extraction lemma, which says that from every Lie chart, a provable solution can be extracted. Let's call it E0. And now the lemma that I have not yet explained to you, it says that solutions can be pulled back conversely along functional bisimulation. So E0 is a solution of C0. E0 is also a solution of C of E1. It's the start value of a solution of C of E1. And also E0 is the start value of a solution of C of E2. Now, finally, we use that all provable solutions of Lie charts are provably equal. We can show that E1 is PBP provably equal to E0, and E2 is provably equal to E0. And now clearly we can use transitivity to show E1 is provably equal to E2. We have started from the assumption that the process interpretation of E1 and E2 were bisimilar, and we have concluded that E1 is provably equal to E of E2 in the system PBP. In this way, we have shown the completeness direction of the completeness theorem. Now, finally, I want to explain to you the intuition behind the main lemma. The main lemma says that the bisimulation collapse of a Lie chart is again a Lie chart. Here, the idea is to prove that not by a single step towards the bisimulation collapse, but by identifying collapsing charts point by point, by taking pairs of bisimilar but distinct vertices and collapsing them one after the other. So in this chart that you see on the right, I have highlighted in magenta a pair of bisimilar vertices. What now happens is that all the incoming arrows to V0 are being moved over to V0 double prime, which in this case is just the arrow that signifies the start vertex. Then this is a transformation of the form 1 that we call our transformation 1. Then we have here other two distinct bisimilar vertices. They are collapsed by redirecting all incoming vertices at V1 over to V1 prime, being here done, and also introducing a loop entry label, which is indicated here in red. And then we are in a situation that we use a third transformation, and by which we have actually obtained the bisimulation collapse, which is of a form that you've already seen via an isomorphic transformation. And now the basic idea of our proof consists always, if a chart is not a bisimulation collapse, a Lie chart is not a bisimulation collapse, then we can find bisimilar vertices to which we can apply one of these three transformations. A corollary of this lemma is an important result, namely that a chart is expressible by one free star expression modulo bisimilarity if and only if its bisimulation collapse is a Lie chart. This is actually a criterion which is recognizable in polynomial time. So in order to conclude, let me remind you what we have done. We have obtained a partial solution of Milnor's problem by looking at an adaptation of Milnor's system to one free star expressions, and that was the system by Bergstra, Bethke, and Ponce. We importantly introduced a loop existence and elimination property, which made it possible for us to guarantee solvability via extraction. It holds for the chart interpretation of one free star expression. and it is preserved under bisimulation collapse. With this, we could show our completeness result. Now, what is the obstacle for extending the same reasoning to Milnor system? It is perhaps possible, but it must be more complicated to apply it to Milnor system because the two properties I and C do not hold for all star expressions. There are interpretations of star expressions with one and unary Kleene star that are bisimulation collapses but do not satisfy Lie. A possibility to deal with that would be to use a workaround, and this would mean the use of one-charts, charts with explicit one transitions. I have actually done so in an extended abstract for the term graph workshop on July the 5th to make a first step in this direction. I also want to refer you to the report version of our article with all of the proofs of the transformations. And with doing so, let me please thank you for having me and thank you for your attention.